We are going to practice classifying our types of reactions. And what we have is we have 5 sets of reactions. On this sheet, this little box should have been our yield arrow. So you can put a yield in there so you know which side is your reactants and your products. And the first thing that I always ask my students to do when they're given a bunch of reactions is to pull out the combustion reactions. Combustion starts messing with people's heads. They think they're double replacements, single replacements, all these things. So if we get rid of those first, then we know how to do the rest. So what are we looking for? We are looking for oxygen on the left side of the reaction. And this is a pattern, so we should have oxygen on the left side everywhere. Here, we do have some oxygens, but not in every single one. So this whole group cannot be categorized as combustion because some of them are not. Over here, we have oxygen on the right side, so it makes it a product. That is not a combustion. A combustion has to be on the left side, and it has to be a reactant. Okay, I don't see that here. I don't see that here. And what we do have is we have oxygen, O2s, as reactants all the way down. We have different numbers of those diatomic elements, but we do have oxygen as a reactant for all of these. So we have our reason is O2 is a reactant, and this makes it combustion. Okay. Now, the other thing to notice is we are burning or combusting hydrocarbons. We have hydrogen and carbon all over here. And if we are burning or combusting hydrocarbons, you need to understand that it will always make water and carbon dioxide. These can be in any order. I could have wrote carbon dioxide and water as long as they are all products on the right side. Okay, so when we combust hydrocarbons, we are making water and carbon dioxide. So I want you to pause the video and see if you can, on your own, find all the rest. And then we'll come back and we'll do an explanation of what's going on. Okay, how do we do? Well, our first two sister reactions, I'll make this a little bigger, is synthesis and decomposition, and they happen to be on both sides. How did I figure that out? Well, I have two things forming one thing on this side, okay? Now, yes, our coefficients say there's multiple, but there's multiple of only one type of compound all the way down here. So when we have two things coming together and forming one type of compound, that's going to be our marriage or our synthesis. And we only have one product, okay? That's one product on this side. Yes, I know people like to say there's two iron or iron oxides, but there's only one type of product there, okay? The reverse is we have one type of reactant and they break apart into pieces. Okay, so we have decomposition, we're breaking apart. We only have one type of reactant, and so that makes it a decomposition, okay, at this level of chemistry. And our last two are our single replacements and double replacements. Remember, for our single replacement, we're looking for a single element in a compound on both sides. It's the type of thing. I could have multiple single elements and multiple compounds with those coefficients, okay? But we're looking for something with one capital letter, something with two or more capital letters there. So over here, I have two capital letters. I have one capital letter. So that's a compound and an element. Here I have one capital letter and two capital letters, an element and a compound on both sides, okay? Here's my element, here's my compound, here's my element, here's my compound. Chlorine is a diatomic element. There's only one capital letter there, and this has two capital letters. It's a compound, so an element and a compound. Two capital letters is my compound and an element. So single replacement because I have an element and a compound on both sides. Versus our double replacement where we have two couples going to the dance, so I have two compounds. How do I know that? Two or more capital letters on that side for each species. Two capital letters, two capital letters. That's actually three because we have that polyatomic ion going on there. So we have two compounds on both sides. And if we check, it's all the way down. Two compounds, two compounds, two compounds, two compounds. And that is a very easy way to see all kinds of different types because we have these groups. We have multiple of the same kind of reaction.